So we begin our look at mechanics with a discussion of kinematics, which is really the study of how motion happens. And this should be, to some extent, a review of some of the highlights that were learned in our introductory physics course, the grade 11 course. And so what we're going to do is we're going to work through several very typical problems as we progress and review and learn a little bit more as we go. So one of the things that we want to remember is the 5 kinematics equations that you can see listed here. And it's important to remember that these equations were all derived from a simple velocity time graph with uniform acceleration, or with a constant acceleration. And so as we proceed, we have to remember that if we ever encounter a problem or a situation where we don't have a constant acceleration, then we need to do something a little bit different. If we have a changing acceleration, we can't use these equations at all. If we have a problem with multiple different accelerations, then we'd have to divide the problem up into different groups. And so a couple of comments about solving problems in general, as we will see. First, it's important to set up sign conventions at the very beginning of the problem and then stick with them throughout. So pick which way you want to be positive and which way you want to be negative, either up, down, left, or right, and then stick with them for the entire problem. It'll make life way easier. The second little pointer here is to make a wise choice of equations. And I think we've all had the experience where we start out to try and determine a variable, and we end up using maybe 2 equations, maybe 3 equations, when really if we had made a wise choice, we could have perhaps picked 1 equation and it would have done the job for us right away. By this point in your academic career, you probably have developed your own strategy for solving problems. In grade 9 and in grade 10, we'd tell students to use something like the guess method, where we list our givens and our unknowns, our equation that we're going to use, the solution, and then a statement at the end. And here we are in a senior physics course, senior high school physics course. We're not going to insist that you use any type of strategy specifically, but that you use a strategy that makes the most sense to you, the learner. And that's really, really important because by this point you've probably developed your own style, so stick with that. Last but not least, don't ever forget your units, and at the end of every single problem, always do a sig fig check. So with these little tips in mind, let's take a look at a couple examples. So here's example 1. A marathon runner accelerates uniformly at 0.2 meters per second from an initial velocity of 3 meters per second. How long will it take the runner to travel a distance of 12 meters? So we pick our sign convention, and this way we'll just stick with the normal, that positive would be in the right direction. And then we have acceleration equals 0.2 meters per second squared, which was given. Our velocity, our initial velocity, v1, would be 3 meters per second. And we're interested in how long it will take the runner to travel a distance of 12 meters. So t is our unknown. We can say, okay, well, a wise choice of equation would be this one here. And what we can do is we notice right away, oh, this includes all of our unknowns, and it includes all of our givens, which is very nice because in one step we'll be able to solve this. And so we now substitute our numbers in, and we get 12 is equal to 3t plus 1/2 times the acceleration times t squared. And you may be able to forecast what's coming if we rearrange 0.1 t squared plus 3t minus 12 equals 0. This is, of course, a quadratic. And we will use then the quadratic equation to solve it. Just for a reminder, this is the quadratic equation. And we can substitute our numbers. We know that the quadratic, of course, because of its nature, will produce two roots. And in this case, the two roots are 3.5 seconds or negative 33.5 seconds. And we need to make a decision, okay, which root do we take? In this example, it makes the most sense to take the positive root because a negative root for time is inadmissible and really makes no physical sense. So we select the positive root in this case. Now we have to be very careful because sometimes students can fall into the trap of only selecting the positive root, but that can be dangerous, especially when we're dealing with quadratics where time is not our variable. Perhaps velocity is our variable, or another term altogether. We have to be very careful. Don't fall into the trap of always selecting the positive root, because sometimes the negative root actually does have a physical interpretation and is important. But in this case, we can say that for this marathon runner under these circumstances, it'll take 3.5 seconds to run a distance of 12 meters. Example 2. A Jeep accelerates from rest at a rate of 4 meters per second squared for 10 seconds. It then travels at a constant velocity for 12 seconds and then finally comes to rest over a displacement of 100 meters. Determine the Jeep's total displacement. So what we have in this case is we have a Jeep accelerating for a certain amount of time, and then it travels at a constant velocity, which means it's not accelerating. So its acceleration has changed from the first 10 seconds to the second stage, which is really for 12 seconds. And then finally comes to rest over a displacement of 100 meters, which is a third acceleration, because if something is traveling at a constant velocity and then comes to rest, it's decelerating. So we have 3 different accelerations in this problem. And of course the caution is that we need to now divide this problem into 3 different stages because of the different accelerations. So we break it up. Stage A, Stage B, and Stage C. And so now let's take a look at this. What we have in Stage A is we have a velocity initially of 0. We know the acceleration, we know the time. Because we're asked to find the total displacement, that's of course one of our unknowns, but also if we want to consider the displacement for Stage B, we need to know how fast the Jeep is going at the end of the first stage, because that will be the new constant velocity for Stage B. And that's of course what's noted here is that the velocity at the end of Stage B is equal to the velocity at the beginning of Stage B, which is actually equal to the velocity at the end of Stage A. And of course the time for this stage is 12 seconds. And then finally in Stage C, we know a few things. We know that it comes to rest. We could probably find the acceleration. But really, those things aren't going to be important because we're just looking for the total displacement. And the last stage, it tells us that the total displacement over the last stage is 100 meters. So that's kind of a gimme in this case. So here we have an equation where we can work out the velocity for at the end of Stage A. And so we'll just use V2 equals V1 plus AT. And the subscripts may at first seem confusing, but of course we have the subscripts that are looking at specifically just the Stage A that we're interested in. So we know it's going 0, acceleration is 4, and the time is 10. So at the end of Stage A, we're traveling at 40 meters per second. Also, we can find the displacement from stage A, and we'll use this equation to help us with that. Initial velocity of 0, we know the acceleration, we know the time, and so we can say, all right, well, we've got 200 meters that it's traveled during that initial acceleration. So let's jump now to stage B. And we just calculated that the velocity at the end of stage A is equal to the velocity during stage B, which is 40 meters per second. And we can work out our distance is equal to velocity times time for this stage, because there is no acceleration, it's just constant velocity. And it travels 480 meters. So now we're at a point where we can say, hey, we want to know the final displacement, or the total displacement, excuse me. We can put everything together. And we can say, all right, well, the total displacement is going to be the displacement of each of the 3 stages added together. And we come up with 780 meters. We do a check for significant figures, and we say, all right, the Jeep travels 7.8 times 10 to the 2 meters. Now, there's a lot of other things that we could do with these types of problems, right? There's a lot of other questions that we could ask. One of them would be to calculate the average velocity, or the average speed. One of them would be to find the acceleration in the final section, etc., etc., etc. So there's a lot that can be done with this, and we've just selected, one thing to do, but there is a lot more that can be done. So now we're going to turn our attention to two-body problems. And we're going to encounter these situations, and really what they are is where we have 2 different bodies that are experiencing 2 different types of motion. And we're usually asked to find, something in common between the 2 of them at the end of a certain period of time, like where do they meet, or when do they meet, or, these 2 bodies are doing this, and what would the velocity have to be if they were going to meet at this point in space? These questions can be very tricky, okay? But there's certain things that we can do to simplify our task. One of them is to adhere to a common coordinate system for both bodies. So we're going to lay down a coordinate system and then stick with it for body A and for body B. And with that coordinate system, we have to use the proper sign conventions. And that should help us through. And so there's a couple of examples here. We have Clyde and Delilah. And they're at the opposite ends of a very, very long 1-kilometer hallway. And so we have one body, Clyde, and he accelerates from rest towards Delilah at 2 meters per second squared. And at the same instant, Delilah travels towards Clyde at a constant velocity of 10 meters per second. And how much time passes before they meet. So here's a little diagram of the situation. We're going to set positive to be in the right direction, and we're going to put Clyde at 0 on our coordinate system. And they're going to meet at some point in space. And we just call it D star. It's a special displacement because it's where they meet. If she's at the opposite end of the hallway, then of course she is sitting at 1,000 meters. And now we're set to go. So let's take a look at the equations that we have for Clyde. He's accelerating. He starts at rest. We're interested in displacements. We're interested in time. So we're going to use this equation. And it's simplified, which is nice because we have a velocity of 0. And we can see, an initial velocity of 0. We can see that Clyde has a final equation. He will meet her when his displacement is equal to his time squared. Okay, so we're going to call that equation 1. And we got that by subbing in. Now, we don't have enough now to continue, so we need to look somewhere else. And the other place that we're going to look is, of course, her and what emotion she's having. And so we can say, okay, well, what's going on now with Delilah? Well, she's starting at 1,000. She's ending at where they meet. So d2 minus d1 is her displacement. So d2, which is d star, minus 1,000. And that's equal to velocity times time, because she's not accelerating. But her velocity is in the opposite direction, because she's running towards Clyde. And in our coordinate system, with our sign convention the way it is, we have to enter that velocity as being negative. And so that's what we get. And here's equation 2. So we have two equations, and we have two unknowns. And we can solve two equations and two unknowns. Let's just set equation 1 equal to equation 2. And we end up with t squared is equal to minus 10t plus 1,000. Because we have d star on the one side, we have d star on the other side. Let's just eliminate it all together. And this, of course, if we rearrange, is a quadratic. And we can use the quadratic equation to solve it. Okay, so subbing in our numbers, here's what we'd get. And of course, we'd get two roots. One of them is a positive root, one of them is a negative root, 27 seconds, or negative 37 seconds. Again, in this case, the negative root does not make sense, so we stick with the positive root. And we say, well, these two are going to meet after 27 seconds. A very good follow-up to this question is, where do they meet? And we could go back now that we solved for time, and we could figure out the displacement. A special type of two-body problem is the chase problem. And this is where one object follows or chases another. And what will often be asked is, do they meet? If so, when and where? And if they don't meet, how close do they get? A car traveling at a constant speed of 45 meters per second passes a police car behind a billboard. 1 second after the speeding car passes the billboard, the police car sets out to catch it, accelerating at a constant rate of 3.00 meters per second squared. How long does it take until the police car catches the speeder? So again, we have to be very careful about our sign conventions here and our coordinate system, because we have two bodies. So we'll pick positive to be in this direction, and we'll say, okay, well, once the police car starts moving, after the 1 second head start, this is what we've got. We've got the police car, which is white, and the speeder, which is kind of shaded in there. And the speeder's got a head start. We also know that the head start is exactly 1 second. And then sometime later, the police car and the speeder have the same location. So it's sometime later on, the police car's caught up. Now in this case, the problem actually tells you that the police car catches the speeder. And so we can say, okay, well, let's answer it under that assumption. The first thing that we need to do, though, is we need to work out the distance, the head start. Instead of having the head start in just time, let's work out the head start in distance. And so we can say that, okay, well, we know that the speeder is going at constant velocity. And so if he's going at constant velocity, we can just say distance equals velocity times time. And if the velocity is 45 meters per second and it's a 1 second head start, this translates to a 45 meter head start. Say, okay, fair enough, that's good to know. So now we'll come back and we'll say, okay, let's look at the police officer. He's accelerating, or she is accelerating, at 3 meters per second squared. We start at a velocity of 0, and we end some distance later at d. But because we've set the police car's initial displacement to be 0, then what we have is, again, a very simplified equation. that displacement is equal to 1.5 t squared. And we're going to call that equation 1. For the speeder, we have something similar, but the speeder has a head start, does not have an acceleration, and is traveling at a constant velocity. So the head start for the speeder is 45 meters. So d2 is further on down the road, minus d1, which is 45, is equal to 45t, and we're going to call this equation number 2. And again, we can sub the value for displacement in equation 1 into equation 2 by setting the two equations equal to each other, and we end up with 1.5t squared minus 45t minus 45 equals 0. Again, this is a quadratic. It's very important that you know how to use the quadratic equation. And of course, if we solve this, and we're not going to do it here, we've already done 2 examples with it, we find that the time it takes for the police car to catch the speeder is 31 seconds. And a great follow-up or a great B part to this question would be, what is the distance that they have to travel before he catches up or before the police officer catches up to the speeder? That would be a great follow-up question. And of course, that's very easy to do. The last type of problem really that we want to look at are bodies in free fall. And these are very, very common problems. Often you'll see questions where you have a ball that's thrown straight up into the air, or let's say a stone dropped from the top of the CN Tower, etc., etc. And we cover these in great detail in the grade 11 course, and we're going to look at a short review of those things here. Because now we might be able to do chase problems or two-bodied problems with things in free fall, which is another wrinkle. So here's example 5. A baseball is thrown straight up in the air, leaving the thrower's hand at an initial velocity of 8 meters per second. How high does the ball go, and how long does it take to reach that height? So here's a little diagram of our situation. We're going to say that up is positive. The ball goes straight up and comes straight down because this is motion in one dimension. If it didn't go straight up and straight down, it would be motion in 2 dimensions because then it would translate in x as well as traveling in y. We're not interested in that. That's lesson 4 later on this unit. So here we have our little diagram. And we say, okay, well, we know that v1 is up at 8 meters per second, right? Because it leaves with an initial velocity of 8. We know that the acceleration due to gravity is down, which would be negative in this sign convention, and it's 9.8 meters per second squared. That's not enough information to solve for much, but what do we know about the velocity of a ball at its maximum height? And that should be a pretty standard review question. Most of you should be saying, oh, well, at its maximum height, its velocity in the y direction is 0. So if we want to say how high does the ball go, we can say, well, we know at the maximum height we have a velocity of 0. So we can say let's use that to determine the height. And we can simply say v2 squared minus v1 squared equals 2ad. We can substitute some of our numbers in. And this is very nice because, of course, the displacement should be positive. And we can see that our 2 negative signs will cancel. And we get 3.27 meters up in the air. Then we want to say, okay, well, how long does it take the ball to reach that height? And we could either use the displacement that we've just found, or we could use the exact same information we had at the beginning and just a different equation. v2 equals v1 plus at. And that's what we'll do. Substitute in some of our numbers. And once again, it's very nice because the negative signs cancel out because our sign convention is intact. We get time equals 0.82 seconds. So that's a little review question. Our last question, again in free fall, a rock is thrown vertically upward from the cliff, from the edge of a cliff, at an initial velocity of 10 meters per second. And it hits the beach below the cliff 4 seconds later. How far down from the top of the cliff is the beach? So here's our little diagram. And the rock goes up to a maximum height and then falls. Now, the nice thing is that we don't have to worry about how much time or the distance to the top. We could do that. Find the distance to the top and then the distance from the top all the way to the bottom, but we don't need to do that because our equations are set up in such a way that all of that will be taken into account for us if we use the proper equations. So here, sticking to our sign convention, the initial velocity would be in the upwards direction because it's thrown up. Acceleration is, of course, down. And the time is 4 seconds. And because we've looked specifically at 4 seconds, that's the time from when it leaves the hand until it hits the beach. And because everything's based on these kinematics equations, which are quadratics, right? That time will be just fine. It will be just enough for us to say, okay, this knows the math will come out correctly because the equations that define the physics are correct. So we can say, let's use d equals v1t plus 1/2 at squared. And we can substitute in our numbers. And we get minus 38.4 meters. Which is very nice because we set 0 in our coordinate system to be at the top of the cliff where the motion began. So that's 0, then minus 38.4 is of course down 38.4 meters, and that's where the bottom of the beach is, 38 meters below the cliff. And that is motion in one dimension, as you need to know it.